We are a group of third-year mechanical engineering undergraduates from the University of Peradeniya, and this is our group project titled Mini Channel Condenser Performance in a Refrigeration System Using Propane as the Refrigerant. Hi, everyone. In this presentation, we'll be demonstrating our project focused on analyzing the two-phase region of a mini-channel condenser using propane as the refrigerant. In this project, propane is selected as the refrigerant due to its low global warming potential, excellent thermodynamic properties, and high latent heat of vaporization. It is also a natural refrigerant, making it an environmentally friendly alternative to synthetic refrigerants like R134A or R22. Mini-channel condensers are chosen because they offer a higher surface area to volume ratio, which improves heat transfer performance while reducing the size and weight of the system. These compact condensers are ideal for space-limited applications, such as automotive air conditioning or small-scale refrigeration systems. Each dataset contained 12 segment-wise temperature readings along the condenser length. First, we fitted this data using sixth-order polynomial curves to smooth the profile and prepare it for further calculations. Using this, we calculated enthalpy values at different points, allowing us to identify the subcooled, two-phase, and superheated regions. However, our project focuses only on the two-phase region, since that's where the refrigerant undergoes phase change and contributes most to heat transfer. Once the two-phase region was identified, we performed calculations to determine the heat transfer coefficient. We used the water-side temperature difference to calculate the log mean temperature difference, or LMTD. Then, using heat gain by water, we calculated the overall heat transfer coefficient and finally derived the experimental heat transfer coefficient for the refrigerant side. We began by calculating the log mean temperature difference, or LMTD, which is essential in determining heat exchange efficiency. The LMTD is given by the formula how LMTD, where delta T1 is the temperature difference between the refrigerant and water at the inlet, and delta T2 is the temperature difference at the outlet. These values were calculated for each segment using the polynomial fitted temperature profiles. Next, we calculated the overall heat transfer coefficient, denoted by U. The heat transfer to the water side was calculated using the energy balance equation. Q equals M times Cp times delta T, where M is the mass flow rate of water, Cp is the specific heat of water, and delta T is the water temperature rise. Then the overall heat transfer coefficient was obtained by rearranging the equation Q equals U times A times LMTD. Solving for U equals Q divided by A times LMTD, where A is the heat transfer surface area. After obtaining the overall U value, we calculated the water side heat transfer coefficient alpha 2. We assumed single-phase flow for water and used the Nusselt number correlation, where K is the thermal conductivity of water and D is the hydraulic diameter of the mini channel. The Nusselt number was obtained using empirical correlations based on laminar or turbulent flow conditions, depending on the Reynolds number. Finally, using the relation for overall resistance in a two-fluid heat exchanger, this allowed us to calculate the experimental alpha 1 values, which were later compared against various theoretical models in the two-phase region. To compare our experimental values, we applied several well-established theoretical models, including Dobson and Chateau correlation, Low-Dian correlation, Nusselt and Kutataladzhi equation. These correlations take into account parameters like vapor quality, flow regime, and refrigerant properties to estimate the heat transfer coefficient. We then compared the theoretical values with our experimental results. For Dobson and Chateau, we considered a 30% margin of error and achieved about 85% match. For the Low-Dian Nusselt models, we used a stricter 15% margin and still achieved more than 85% correlation accuracy. This indicates that our experimental data aligns well with the theory. Our Excel sheets include graphical comparisons of all the models. The closer the data points were to the y equals x line, the better the match. We also calculated the error margins for each model and displayed the results clearly using tables and plots for validation. In conclusion, we successfully analyzed the two-phase region of a mini-channel condenser using both experimental and theoretical approaches. The model validation confirms that standard heat transfer correlations are effective when properly applied. Thank you for watching our project demonstration.